Section 9.6, we have two more tests, and they are our last two tests for convergence, okay? They're the ratio and the root tests, and kind of like with some of the others, there are some sort of red flag things that when we see certain features in a function, they will scream, use the root test, use the ratio test. And so I'll try to draw your attention to those along the way so that when you're looking at them on your own, those kinds of things start screaming at you as well. So we're going to start with the ratio test. So this is Theorem 917. The ratio test, and it says the following. We're going to let the summation of a sub n be a series with non-zero terms. And you'll see in a moment why we need them to be non-zero. But they can be positive, they can be negative, but they just aren't zero. There's three possible things that can happen. The series, summation of a sub n, converges absolutely. And this happens when the limit as n goes to infinity of a sub n plus 1 over a sub n is less than 1. Yep, and the absolute value is less than 1. Okay, so the limit of the absolute value is less than 1. It will converge. This is why the positives and negatives don't matter on this too. But you can see there'd be a problem if there's zeros, right? Because if there's a zero term, at some point it ends up in the denominator, and we would have a problem. So we can't have zero terms that are non-zero. The second option or possibility is that the series diverges. So the series summation of a sub n diverges. And this happens when the limit as n goes to infinity of a sub n plus 1 over a sub n is greater than 0, or if it's infinity, which obviously is bigger than 0 too, but your book does a distinguishing factor for that, so I will as well. That shouldn't say greater than 0. I apologize. That should say greater than 1. I was looking at another part of my screen or my paper. Okay, greater than 1. So less than 1, it will converge absolutely. Greater than 1 or infinite, it will diverge. So the question is, what happens when it equals 1, right? What's going to happen? And you might think, well, the third option we had last time was converging conditionally, and it would seem like a logical thing that would happen next, but it is not what happens next. What actually happens is that when it equals 1, the ratio test is inconclusive. So the ratio test is inconclusive when the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1. So it doesn't necessarily mean that it converges. It doesn't necessarily mean that it diverges. It could do so, either of those things, or it could do so conditionally, but we don't know what it does. Really what this is telling you is that the ratio test was not the test to use. Okay? It wasn't a good choice. It didn't work to actually give us any information. So we're going to do a couple of examples. So we're going to determine the convergence or divergence of the series. So obviously I'm showing you these two examples because the ratio test is something that is likely that you would try given the descriptions I'm going to give you. And I want to show you what happens when you try it. So this is n equal 1 to infinity of negative 1 to the n times 6 over n factorial. Okay, so factorials. Jot yourself a note. Factorials tend to work really nicely with the ratio test. And I'll show you why. So our goal is to take the limit as n goes to infinity of the absolute value of, let me make it big, negative 1 to the n plus 1 times 6 over n plus 1 factorial over negative 1 to the n times 6 over n factorial. So if we're really going to write it all out, that's what it would look like. But there's some pieces of this, one piece in particular, that's really not necessary to write. Do you know what it is? Yeah, these pieces right here don't matter. Why not? Because we have the absolute values. And you probably sort of thought that when we were working with the alternating series tests last time, right? And some of the absolute convergence things. If you're taking absolute values anyway, the negative 1 to any powers just don't matter. So if you wanted to, you could have done this. Let me see if I can delete it now. Oh, I didn't want to do it that way. So that it only had the 6's in there on the top. Okay, so it would be perfectly reasonable to have never written them to begin with. All right, so taking a look at this then, complex fractions, right? Fractions inside of fractions are not super nice. So instead of dividing by that second fraction, what can we do? Yeah, we can multiply by the second one, right? So we have 6 over n plus 1 factorial times n factorial over 6. What do you notice? Okay, 6's cancel. Yeah. So I'll write it out just a little bit, but n plus 1 factorial means n plus 1 times n minus 1 all the way down. So it actually can be thought of this way, which means the n plus 1 is the only thing that remains in the denominator. So this becomes, this equals, the limit as n goes to infinity of 1 over n plus 1. You can write the absolute values if you want. It doesn't necessarily matter because we're putting in positive terms, so if you left them off, it'd be okay as well. What's going to happen to this as n goes to infinity?
0.
Yeah, this is going to equal 0. So of our 3 cases on the top of this screen, which case are we in? Yeah, the first one. It's absolutely convergent. So that's what we're going to say. Thus, by the ratio test, the summation from n equal 1 to infinity of negative 1 to the n, times 6 over n factorial. Oops. Let me just write it the way they have it written. Converges absolutely. Okay, so can you see why factorials work so nicely for ratio tests? Yeah, they really do. So anytime we see those factorials, you should just have this, screaming voice in your inside of your head that says, this looks like a ratio test. All right, so let's try another one. This is another one where there's a key idea that says, it's not factorials, that says we should probably try the ratio test. So it looks like this. It's a summation from n equal 1 to infinity of n times 6/5 to the n. Now, there's no negative 1 to the n power here. So we don't have to necessarily have that in order for it to be used, for it to be a ratio test. But We did on the last one, we did on this one. So this is the limit as n goes to infinity. And we are doing n plus 1 times 6/5 to the n plus 1 over n times 6/5 to the n. In absolute values. Once again, the absolute values don't really matter because this is always going to be positive anyway. So if you wanted to leave them off, it wouldn't be wrong. Why do you think that it might be nice to use the ratio test here? Do you see anything that's kind of conveniently going to simplify?
6/5, yeah.
Yeah, the 6/5 to the n. So if you didn't notice it right away, that's okay. 6/5 to the n plus 1 here would be 6/5 to the n times 6/5, or 6/5 to the 1 if you think about it that way. So n plus 1 being the power can be split up that way. And because it can be split up that way, the 6/5 to the n on the top and the bottom here would cancel. So I would end up having, we'll rewrite this part, limit as n goes to infinity. I have the n plus 1, and I have the n, and I have 6/5, and it's on top, but I'll just write it out to the side. I'll keep my absolute values, but not because it's necessary. Okay, is that all right? All right, so this actually looks a lot like things that we've done limits of before. Not the 6/5 part per se, but the n plus 1 over the n part should. Looks like a polynomial over a polynomial. And the reality is that the n's at the beginning are the important part, right? So if I were to take a look at this and think really all that matters is n over n, and I only looked at the part of it that has this part, just ignore the 6/5 right now, the limit of the part that's the polynomial part, right, the fractional part with polynomial over polynomial would be 1, right? Because I have n plus 1 and I have an n. The plus 1 doesn't matter. It's really like n over n. And the way that we've actually shown that every time to be like accurately working is that we've multiplied the top and the bottom by 1 over n. So our limit as n goes to infinity would have, which one's on top? 1 plus 1 over n over 1 times 6/5. I'll go ahead and leave off my absolute values since I don't need them. But the 1 over n goes to 0. But then I've got the 6/5 at the end, so that gets multiplied. So what's the limit of this thing? It's 6/5. What does that tell us? It diverges because this number is greater than 1. You got, so by the ratio test, the summation from n equal 1 to infinity of n times 6/5 to the n diverges. Okay, so ratio test typically is used when we have powers of n, right, because they're going to reduce like this, or we have factorials. Okay, ready to look at the other test? Okay, the other test is called the root test. This is Theorem 918. It's the root test. And it looks a lot like the last one in the sense that there's these three different conditions, three different like outcomes that can happen. One outcome is that it's going to converge absolutely. One outcome is it's going to diverge, and the last outcome is that it's inconclusive. So those pieces match between these two tests. And they show up like this. The series, summation as n, well, summation of a sub n converges absolutely when the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. So the root test says we're going to take nth roots. And the next option, the series diverges when the the limit, as n goes to infinity, of the nth root of the absolute value of a sub n is greater than 1 or equal to 0. Equal to infinity. Got the wrong thing, equal to infinity. Same piece at the end as the other one, right? As the ratio test. The first one's greater than 1, the first one's less than 1, the second one's greater than 1 or equal to infinity. And so the last one is going to be when what happens? When is it going to be inconclusive? Yeah, if it equals 1. So the root test is inconclusive when the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to 1. Okay. We should do some examples, right? Of course. All right, got a couple of them, I believe. So our second set of examples, using the root test this time, same directions, determine the convergence or divergence of the series. And our series we're looking at on this one is the summation from n equal 1 to infinity of 4n over 5n plus 1 to the power n. Okay, so why is this sort of beckoning us to potentially use the nth root? Well, because it has a power of n. Yeah. And you might be like, well, didn't this last one have a power of n? And it did, but it also had an n as an x or as a coefficient at the beginning, right? Like a constant, not a constant multiplier, but as a multiplier. And that caused us to have sort of a problem. The nth root wouldn't work as nicely on this particular one. So on this one, could we use the ratio test? Yeah, you could. It wouldn't be the worst thing in the world, maybe. But it might not be the best either. The nth root test works really well. The one problem that might show up if we tried to use the ratio test is that while we would have an n plus 1 power and an n power, they wouldn't be of the same quantity inside, right? One of them would be 4n over 5n plus 1. The other one would be 4 times n plus 1 over 5 times n plus 1 plus 1. They wouldn't match. So the nth root test is the root test is a really nice one to use here because we have that power of n. So we're going to take the limit as n goes to infinity of the nth root, and we'll put the absolute values on, but once again on this one they're only positive terms, so it doesn't really affect it. But we have this expression to start with. And of course the power of n and the nth root are inverse operations, right? And we already mentioned that the absolute values aren't really necessary, so if we'd like to, we can exclude them as we write our next step. The limit is n goes to infinity, and we're really looking at 4n over 5n plus 1. What's my next step? Multiply by 1 over n over 1 over n. So this becomes the limit as n goes to infinity of 4 over 5 plus 1 over n. 1 over n goes to 0. So what is this limit? 4/5, which happens to be less than 1, right? So what does this tell you? Yeah, by the root test, right? So by the root test, somewhere in your description it needs to say by the root test, the summation from n equal 1 to infinity of 4n over 5n plus 1 to the n converges absolutely. Okay, I have one more specific example of the root test, and then we're going to change topics just slightly to talk about something else. Try to bring things all together, really. The next one is the summation from n equal 1 to infinity of n over 500 to the n. So again, power of n seems reasonable. We'd use the root test. So the limit as n goes to infinity of the nth root of n over 500 to the n, absolute value. And the nth root and the n power would reduce. So I have the limit as n goes to infinity of n over 500. It's positive, so I've left off my absolute values at this point. What is the limit of n over 500 as n goes to infinity? Yeah, it's infinity, right? I know n over 500 starts out kind of small, right, when n equal 1 and n equal 2. But eventually, n going to infinity will dominate. This will equal infinity. So what does the root test tell us? Diverging, yeah. It's okay. By the root test, the summation from n equal 1 to infinity of n over 500 to the n diverges. The root test is really quick to use, right? I mean, by comparison to the ratio test, which takes us a little longer to work through, it's really quick. So I think that I've rewritten the page number here correctly when I adjusted my notes. Page 632, we'll hope that the number's right, has an excellent summary of the different convergent tests. So if you're looking for a place that kind of just puts them all in one spot, this is the spot. And that's because they're at the end of the list of them now. These are all of them. So what we're really going to do right now, just real quick before I release you to the boards, is that we're going to take a look at 4 different examples. And what I'm going to do is I'm going to write them all down, and you can write them as well. And I want to pause for long enough that you have a chance to look at them and think, what test might I use? I'm not asking you to use the test, just what test might I use to decide on this one. So we're going to name a test that can identify, or at least you could try, it seems reasonable, try, can identify if the series converges or diverges. Okay, so I'm going to write them all down, and I'll just be quiet other than that. Summation from k equal 1 to infinity of e to the k over k factorial. The summation from k equal 1 to infinity of negative 1 to the k times 1 plus 1 over k over k. Summation from n equal 1 to infinity of n to the negative 4/5 and the summation from n equal 1 to infinity of n squared e to the negative n cubed. So after you get all 4 of those written down, take a look at each one and do your best to try and figure out what test do you think you'd try. take about one more minute and see what your thoughts are, and we'll chat. All right, what test do you think the first one might be? What would you try?
Ratio.
Yeah. Jubal, I think that's what you said, right? Use the ratio. So what about it tells you or it makes you think you would want to use ratio?
Factorial.
Yeah, the factorial. Okay, is everybody good with that one? Make sense? Okay, how about the next one? What do you think? What do you guys think? Somebody different. Alternating series. So why might alternating series be a good choice on that one, Caleb?
It's got the alternating -1 at the beginning.
And?
And it's got
What happens to this piece?
it decreases.
Yeah, it decreases, right? It goes to 0. So those two things combined together will make that one work really nicely. Okay, somebody else, number 7. What do you think we might use on number 7?
P-series,
P series. Why would you use a P series, Annika?
as you can be 1 over n to the 4/5 and 4/5 is...
Yeah. Yeah, so that 1 over n to the 4/5. So it can be written sort of in that form that fits that P series description. And 4/5 makes it converge. How about 8? Integration. Yes, this will be the integral test. And in particular, if you're using the integral test on this one, what type of integral are you going to end up, what method are you going to end up using for your integration? U substitution. Yeah, you're right. So those are the different kinds of things we're going to be working with in this section now that we have all of the tests under our belt, as well as simply just using the ratio and the root test that we've already done. All right, so we're going to do some board work. So your homework first, and you can start with the boards on. It's on page 637. And it's numbers 9 through 14. And then 17, 20, 25, 26, 40, 41, 44, and 47. And this is part 1. There will be additional problems inside of this section that we'll be doing on the board on Monday. So do your best to get this done over the weekend, but it won't be collected because I'll be doing 9.6, like we're continuing in it on Monday. So this section, along with the additional problems on Monday, which shouldn't generate any homework, you should have time to finish most of that in class on Monday, would be due then on Wednesday, okay? Any questions on that? Okay.